Today we're going to solve systems with substitution. We've done substitution many a time. You've substituted in 4 for x, and then you solve it. It's the same thing. So when we're solving these systems with substitution, you want to make sure one of our equations has x equals or y equals. You want to get one variable all by itself. If you look at number 1, the first equation already has y equals. That's great. This is what y equals. So in the other equation, anytime I see a y, I can substitute in x plus 11. Here's the only spot in the other equation where I see a y. So that's where I'm going to put the x plus 11. And I'm going to put it in parentheses. That's a good idea when you do substitution. So that would be 5x minus this stuff, the x plus 11, equals negative 51. Again, all I did was replace the y in the second equation. And the whole reason I did that was because now if you look at our equation that's left, it's all x's. And we could solve equations that are all x's or all y's. So we go through our multi-step equation. It's like I'm distributing a negative 1 here. So 5x, negative 1 times x is negative 1x. Negative 1 times 11 is negative 11. Sick. After we distribute, we see if we can combine any like terms. I could do 5x minus 1x. It's 4x. 4x minus 11 equals negative 51. And we're having fun. All right. 4x minus 11. You know we have to add 11 to both sides. 4x equals negative 51 plus 11 is negative 40. And then we just have to divide both sides by 4. And we get x equals negative 10. Fun! Looks like a sideways stick figure with a mustache. Yay! All right, fun. All right, now we need a coordinate. That's the x coordinate. We do need the y. So we have to substitute it back into one of the equations and solve for y. Both work, but I always say look for which one looks easier to you. And to me, that first equation looks very easy. So it's y equals x, which we know is negative 10, plus 11. So all I did was substitute in for the x there. Negative 10 plus 11 is 1. Now we've got our coordinate ready to go. The x was negative 10. The y was 1. There's our solution. And remember, the solutions are, if we were to graph these two lines, where would they intersect each other? They intersect at negative 10, 1. But luckily, we don't have to graph them anymore. Okay. Number 2, we try to get x by itself or y by itself in either equation. Sometimes you got to do work. Number 2, they gave us a nice little gift too. We already have x all by itself. So when I see an x in the second equation, I could substitute in 6y minus 8. There's the only spot where there's an x. Put it in parentheses. 2 times 6y minus 8 minus 12y equals 5. We just replaced the x in the second equation. So we'll go ahead and distribute. That will give me 12y minus 16 minus 12y equals 5. We try to combine our like terms. 12y minus 12y cancel out. So all I have on the left side is negative 16. All I have on the right side is 5. Oh my gosh. Does negative 16 equal 5? No! So this is one of those special ones. The no solution or the infinitely many solutions. This is not true. So we say no solution. If we were to graph these lines, they would be parallel lines. They would never intersect each other. That's why there's no solution. Heck, let's try 2 more, huh? This is almost too much fun. I hate to see it end. Oh my goodness. Number 3, y equals. Hey, we got y equals 3/4 x plus 6. Let's go ahead and substitute that into the other equation for the y. 3x plus 2 of those equals 48. All right. We can go ahead and distribute. Now, when we're doing a whole number times a fraction, remember you multiply the whole number up top. So that would give us 6 over 4. If we reduce that, that would be 3 over 2 x. Then 2 times 6 is 12. Now, if you want, you could turn 3 over 2, or turn that into a decimal. 1.5, it still works. But we're cooler than that. We know how to clear out fractions from equations. You just multiply the entire equation by a common denominator. There's only one denominator, 2. So if we multiply this whole equation by 2, there won't be any more fractions. 2 times 3x is 6x plus 2 times 3 over 2. Well, 2 times 3 is 6, divided by 2 is 3. Look at that, no more fractions. Oh. 2 times 12 is 24. And 2 times 48 is 96. No more fractions, we're having fun. Combine our like terms, everyone. Hey, it's going to be 9x. Time to get serious. Can we get serious for a moment? 9x plus 24 equals 96. Now what? Yeah, subtract the 24. You got it. 9x equals 72 divided by 9. And we got x equals 8, baby. That looks like an angry block from Mario Kart if you look at it from the side. Now that's x. We still need y. You can use either equation. Let's get wild and use that first equation. Y equals 3/4 x, which we know is 8, plus 6. Now 1/4 of 8 is 2, right? So 3/4 of 8 would be 6, plus another 6. That means y is going to equal 12. So writing it as a coordinate, our x was 8, our y was 12, so our final answer would be 8, 12. That would be where they would intersect each other if they were both graphed. All right. Don't get too sad, but there's just one more. Here we go. X equals. We didn't even have to do any work to get x by itself. This is going to go in place of x. 3 of those. 5y plus 2 minus 15y equals 6. We distribute. No big deal. Nothing to cry about, guys. 15y plus 6 minus 15y equals 6. Oh my goodness, combining like terms. I got 15y minus 15y. It's almost as if they've been eliminated. So all we're left with is 6 equals 6. This is one of those special ones. Does 6 equal 6? Yeah. So is that no solution or IMS? You're like, Mr. Plant, come on, man. Don't mess around. It's IMS. Infinitely many solutions. If you graphed them, those lines would perfectly overlap each other, touching each other, intersecting in infinite little decimals. And it's so much fun. Look at us. Good job.